let me just give you some background. So, first of all, thank you to Mark and Victoria for having me here today, and thank you all for coming. I was hoping for 3 or 4 people.
We got you 3,000-4,000. Is that okay?
So I have to. My background. I'm professor of quantum information science at the University of Leeds. I've been working in quantum computing since before it was called quantum computing. I started out my career in quantum optics, and then it slowly morphed to quantum computing. So essentially, what I've seen is we went from when I wrote my thesis, when I wrote my PhD thesis. We didn't have a language to describe anything that we were doing. I wrote a PhD thesis this thick to describe something that you all did in the first day. It's 2 lines of quantum computing code to do my entire thesis. And I was having to describe, I didn't have a language to describe it. The language now is quantum information science, and we have a formal language. We can put everything together with that. This language is so nice, and it's so easy to use. We can actually start to describe much more than just quantum mechanics. So we're actually at the point now where things like, let's say, entropic gravity is actually using the language of quantum information science to formulate a new theory of gravity. So what I wanted to do, so this is now my apology. I had prepared a talk aimed at thoroughly the wrong level, to the wrong audience. And I've realized over the last few days that I need to prepare a much better one and put a little bit more work in. And so what I did was I prepared now 3, and last night where I woke up at 3 o'clock in the morning, I'm still on UK time, you see, and rewrote the whole thing again. So what you're going to get is live writing here, what Mark just called hardcore, what I call not being able to use PowerPoint. Okay, so yesterday somebody put up, don't not work. Don't not work. I have completely fallen in love with this remarkable, by the way. It's not an ad, they're not paying me for this. But, okay. There we go. All right. So, yesterday we saw that one of the circuits that you're using quite a lot is this one, the control knot experiment, the control knot circuit. And yesterday I saw somebody rewrite this circuit like this. So if I have an X, so I call this an X, this is a Y, we have an X here, and this is Y O plus X. And then we have exactly the same thing here. We have an X, we have a bifurcation here, and put a Y in here. Quite obviously here I get a Y O plus X and an X. Now these 2 gates do the same thing logically, but they're actually entirely different things quantumly. The reason why they're entirely different things quantumly is because this gate here loses information. So what we have is 2 bits coming in and 1 bit coming out. So this gate has no choice but to dissipate energy. And there's a whole theory of this, and the theory is called, the theory is written by Landauer, and the idea is it's the theory of bit erasure, and this releases, and this is going to be the only formula I write here, this releases kT log 2 of energy. Does that kind of work?
Yes.
Yes, okay. So this releases kT log 2 of energy. Now, the circuit on the other side over here, this circuit looks to be very, very similar. I've got an input coming in here and an input coming in here. But actually, if I rewrite this circuit a slightly different way, and this is the way that almost all quantum information science, this is almost the way that almost all quantum computers work, is I can rewrite this circuit like this. And what this is doing, this gate here is a CZ gate. The one up here obviously is a CX gate. The CZ gate, if I have a 1 at the top up here, I get a loop down here. If I have a 0 at the top, I get no loop. Now a loop in quantum mechanics, this is as quantum mechanics as it gets, this gate. A loop in quantum mechanics adds a phase. So I go from here, down, around, and back. I've added, right? I've rotated my state. So I come down here. Every time I go through a loop in quantum mechanics, I add a phase. This is why they say, for example, that you have to rotate an electron twice to get back to the front. Because you rotate it once, it's added a phase. You've got to rotate it again to get rid of the phase, right? So come down here. There's my phase. And so this quantum mechanical circuit doesn't change energy. I've got no change in energy. The state that came in is the same state that comes out, but I've added a quantum mechanical phase. I use these two gates here, the two Hadamard gates. Then what it does, this is what my students call the block sphere dance. I'm up here, we come down with the Hadamard gate, we do a phase like this, right? And then we come back again with the Hadamard gate. But now, because I've added the phase, I can't come back, I have to go down here. So it's a control knot, but it's a control knot through several steps. But what you can see is that there's no change in energy. And so there's no dissipation. And the benefit of quantum mechanics, the benefit of quantum computing, at least the original benefit, if we go back to the original Deutsch introduction of what quantum computing should be, the original Deutsch introduction said that the idea was that you could do computing without having to erase bits. And so the amount of power that your computer would use is considerably lower than the amount of power that a classical computer would use. If I go back to, I can't remember when they released it, but Blue Gene, the IBM Blue Gene computer, when IBM released Blue Gene, they claimed it to be the fastest computer that was possible to make, because as the power of the computer went up, the air conditioning power went up, and Blue Gene hit the point at which it cost more to run the air conditioner than it did to run the computer. So IBM, that was the point at which IBM put a lot of investment into quantum. Because what IBM wanted to do was move move the air conditioning line down in order to make it cheaper to run supercomputers, right? And that all comes about because of this gate. This is what makes it universal. Now, I can turn this into an atomic clock. An atomic clock is exactly the same thing. I have a Hadamard gate, I have some loops that the atom does, and another Hadamard gate. And the control is time, up here. And so this is an atomic clock. These, by the way, if you're in an atomic clock, these are called Ramsey fields. Ramsey won the Nobel Prize for coming up with this idea. And these up here are called Rabi oscillations. And Rabi was Ramsey's supervisor, and Rabi also won the Nobel Prize for that as well. So this atomic clock is essentially the same thing whereas the control is time. Now, what I wanted to do is just briefly touch on Landauer here, because this Landauer thing is quite useful. So what Landauer says is that in this gate here, we've got 2 bits of information in here, A and B, and we've got 1 piece of information here. We've destroyed something, we've released KT log 2 of energy here. Now, that KT log 2 is really the minimum that you could lose. So if I call this my logic 0, this noise here is the KT, that's the KT thermal noise. This formula is saying that the minimum amount to separate these two, if this was a 1, would be to move it just above the 1 just above the noise. In reality, we don't move it just above the noise, which is only a few microvolts. We move it to 3 or 5 volts, right? So we move it thousands of times above the noise. So an actual classical computer, like IBM Blue Gene, actually consumes about 5,000 times as much energy as it would in the most natural state. On the other hand, a quantum computer at the same time doesn't rely on this. This is not what a quantum computer is looking for. We can manipulate data in a quantum computer without changing the energy. And so we lose this energy consideration here. Now so actually most of you will have seen this. The thermal overload comes from when you overclock your computer, the processor gets hotter, you have to cool it down. That's the extra cost of bit ratio that you're having to pay for that. And so because quantum computers have become faster since IBM released Blue Gene, since classical computers have become faster since IBM have released Blue Gene, as far as I can see, they must already be combining some kind of quantum element in order to make them go faster, for less air conditioning cost. You can do the calculation, actually. You can find out that a computer running a few thousand nodes at a few terahertz, the bit erasure cost adds up really fast. Okay. Now the other thing we can do here is we can actually use what this does is leads us into a whole area called information entropy, right? So can I just have a show of hands? Who's heard of Shannon entropy? Enough. Okay. Shannon entropy is a way of measuring information disorder. The more disordered some information is, the higher the Shannon entropy would be, in exactly the same way as the more disordered a gas is, the higher its entropy is. Entropy is the thing that most of you will have heard of and everybody hates. Shannon called it entropy. Shannon asked von Neumann, what should I call my formula? Von Neumann said, call it entropy because nobody understands it anyway. But the thing is that this information entropy, the thing on which we're basing the concept of quantum computing, we can actually use that to solve problems in regular thermodynamics. So the big problem in regular thermodynamics is a thing called Maxwell's demon. Now Maxwell's demon works like this. I'm going to give you the reduced quantum version of Maxwell's demon. So what I have is a box, and that box contains a particle, and the particle is either on the left or on the right. Now what I'm going to do is say that on the right it's a logic 0, and on the right is logic 1, on the left it's logic 0. Now the demon is able to see the moment at which that flips, at which the particle is on one side. Now if that was an actual bit, what he could do is, rather simply, he could join that onto a resistor, and he could extract KT log 2 of entropy from that, because the logic 1 is above 0, and so he can plug a resistor in and sink that back down from 1 to 0, and he can extract some energy from that. Likewise, the daemon could also see the same thing. If it was on the other side, they could also put it onto a 5-volt rail and sink it down and raise it to a 1. And also, both of these are extracting KT log 2. Both of these are extracting KT log 2 of energy. So all the daemon has to do is see which side that is, and they can always extract energy. Now that seems wrong, right? How could you always extract energy? Now, by the way, in case you're wondering, there are something like 10 or 15 papers demonstrating exactly this. The Maxwell's daemon is a thing that you can actually use Maxwell's daemon to extract energy, useful energy. The question is, where are you getting the energy from? So in this case, it's thermal excitation. I've got thermal excitation from here to here, I extract some energy. I've got no thermal excitation from here to here, and I extract energy. So either way, I can extract energy from this. Now, what I'm missing here is the daemon. So if we write the daemon's memory on the other side, the daemon originally doesn't know anything. As the daemon figures out which side the bit is, the daemon has that in memory. Again, the next time the daemon does it, the daemon has to add one more bit of memory. So we now have 2 bits held in memory. Every time the daemon wants to do that, they have to add more bits to their memory. Eventually the daemon's going to run out of memory space, and they're going to need to start erasing the memory. The cost of bit erasure is KT log 2. So every bit of information, every bit of energy that the daemon has extracted has to go back into the daemon to erase the memory later. And so this is one of the biggest and most outstanding problems in thermodynamics, and it's solved by information theory. There are other areas, and I won't go into this. I was going to prepare. I prepared a whole thing about it. There are other ways that you can do this, and there are other areas. There's another a paradox called Gibbs paradox, and Gibbs paradox is related to cryptography and a few other things. Same paradox, same thing. That the daemon has to erase their energy. So we can essentially we can conclude from that information entropy is actually real energy. Now, what I'm going to do now is take a departure from reality, and I'm going to go into science fiction-ish. There's a theory of gravity. There's a theory of gravity that it's called entropic gravity, and there's a theory of gravity that the dark matter isn't dark matter. The dark matter is actually the information held in the galaxy. Because the information has entropy, therefore it has energy, so it is entropy K log 2, it has energy T log 2, and if we have a lot of information, then an E equals mc squared means that if I have energy, I have mass, right? So if I have a lot of energy, if I have a lot of entropy, and this is a very hand-wavy argument, if I have a lot of entropy, then I can have a lot of mass. Now, the entropy is not in the planet. If I have a planet here, that planet's relatively low entropy. This is a fairly structured piece of stuff, but the rest of the universe is very unstructured. And so the idea is that entropy, what we have is a very high, I'm going to call it S here. So I have S of the universe over here, and I have S of the Earth over here. What I've got is an entropy gradient, which is pushing in this way. So the idea of entropic gravity is that entropy is pushing in. So when I pick something up, I was going to drop my pen, but I don't want to do that. It's too important. If I drop something, but obviously we know it falls down. But the question is why entropic gravity says it was pushed by the rest of the universe. That's strange. Anyway, and then I've got a second formula here. Is that the force is the rate of change of entropy over distance multiplied by temperature. So this formula here, this is sort of standard formula. This is a standard thermodynamics formula. Nothing special about it. But what it does is it links force and temperature. If F equals ma, like it does for Newton, then I've suddenly linked acceleration to temperature. And this is actually, what I'm doing now is entering quantum field theory. In quantum field theory, you can derive specifically a link between acceleration and temperature. It's called Unruh-Davies. If you're interested, if you want to look it up and play at home, Unruh-Davies temperature and the Unruh-Davies temperature comes from acceleration. The second thing, there are two examples. The other example of this is the one that you know about, is Hawking radiation. Hawking radiation comes from essentially the event horizon at Varcoe. This is an interesting, maybe it's interesting to me, obviously. If I accelerate this way, then there's a person behind me, at some distance behind me, who can no longer speak to me because I'm now traveling, I'm now beyond their event horizon. Likewise, if I go this way, there's a person in that direction that goes beyond my event horizon. This is a quantum field theory argument, but nevertheless, you can do it. So if I walk backwards and forwards, what I'm doing is alternately shutting this person out and then that person out, right? Now, that temperature, that acceleration creates an event horizon, and the event horizon is exactly the same as the event horizon created in black holes. But it's just created by me doing this, right? So this is why I'm saying this is. I'm venturing a little bit into science fiction here, but there's a good reason for it, because the idea is that if this is true, right? If this is true, then, and let me just talk about buoyancy for a minute. If I have a temperature inside, if I have a hot air balloon here and I raise the temperature inside of that hot air balloon, the hot air balloon wants to rise, and it wants to rise because it has the entropy inside the balloon is different to the entropy outside of the balloon. We've lowered the density in the balloon, and so it wants to rise. What's really happening is the whole of the atmosphere has been pushed up by the volume of that inside that balloon, and then so it's the gravity acting on the whole of the atmosphere pushing down, which pushes the balloon back up again. Same thing happens when you get into the bath. As you get into the bath water rises, gravity's wanting to push it down and pop it back out of the bath again. That's why you float. Now, this is called buoyancy. Buoyancy is a thing that happens because of entropy, and the idea is that we can have exactly the same thing happen if I have the Earth and I have an object that's accelerating towards the Earth this way. That creates a temperature via quantum field theory. There's a temperature of the Earth, which happens because of Hawking radiation and also quantum field theory, and so therefore an accelerating object would experience buoyancy. Now this is a long way of saying that if you accelerate an object, you might see a shift in time, because gravitational potential is proportional to time. The higher your potential energy, the faster your clock ticks. So if you can modify your potential energy some way by buoyancy, then you've changed how fast your clock is ticking. Right? This is, I'm seeing frowns, that's good, because nobody should believe me yet. So this, now, the thing is that I knew about this theory and I knew what was going on. So this brings me over here to my apparatus. So if you're just kind of sorry for these guys, this brings me over here to the apparatus. So we knew about this, and we knew what was going to happen, and we thought, well, it's really easy to end entropic temperature. We can end this whole entropy argument by building a clock, accelerating the clock, and not seeing a time shift. Unfortunately, we built a clock. We have two HackRFs here. We have two HackRFs and a Raspberry Pi. We're running GNU radio on the HackRFs. We've turned off the phase lock loop between the two HackRFs, and we use instead two different atomic clocks. These are not atomic clocks. These are just precision oscillators, because I wasn't allowed to export the atomic clocks.
We tried.
Yeah, we did try. So I've got two oscillators here. The weird thing that happened is, and this is, I sent a photograph of this immediately to Mark. Mark said, come and talk about it, so I am, is that we saw a shift. We shouldn't. Every theory of physics says there shouldn't be a shift. The only theory of physics that says there should be a shift is entropic gravity. Now, most likely the answer is that we're wrong.
Isn't general relativity also saying that, the further you are into
yes,
there should be a different time shift?
Yeah. That's a really good question. That's a really good question, and the answer is absolutely yes. What general relativity says, and in fact, special relativity, in fact, all the theories say that.
All the theories we checked.
Yeah, all the theories. If I'm here, I see a different time to if I'm here. By the time you get to the height of the GPS satellites are 1 nanosecond faster every second. That makes a huge difference, because it's a foot per nanosecond, so we'd be out by a foot every second. After a year, you wouldn't know where you were anymore. And so what we have to do is what they had to do when they launched the GPS satellites is they had to turn the clocks down so that when they got up, they were ticking faster. So you have to turn them down by half a nanosecond a second. Then you launch them into space, and then they tick faster, and then they're synchronized with us. Right? And then we get GPS. Then we get GPS fixed. Now that's gravity. But gravity isn't acceleration. It feels like it's acceleration. Right? If you drop something, it feels like it accelerates, and certainly we know it's g. Right? It accelerates with g. But that's not the potential energy. The potential energy is something else. Potential energy is g times height, and that only works while g is constant, and then it becomes a problem as you get a little bit higher. Potential energy is g times height, which is slightly different. So what that means is I can have, if I'm on two different planets, I can have the same acceleration but different potential. So I have different time shifts on different planets with the same acceleration. So the answer, the only logical answer that you can get to, is that acceleration itself does nothing. It's the potential energy that does something. And so what you have to do, the only thing that could change time would be a change in potential. Now, I'm not trying to announce this. I'm not trying to say, oh, look what we found. The most likely answer is we've made a mistake. the most likely answer. But if entropic gravity is correct, then we haven't made a mistake. The problem with entropic gravity is that you no longer need dark matter. So if entropic gravity is correct, we've erased like 70% of the mass of the universe. So that was what we're doing. Now we've done the whole thing. The thing is, right, and this is 99% of the reason why I'm talking to you about it. The other 1% is I just like talking. Is that what we're doing here is run-of-the-mill hacker equipment. Almost everybody I've spoken to either has a HackRF at home or knows what a HackRF is, and everybody else knows how to do communication stuff. What we're doing there is actually really, really complicated to a physicist, right? To a physicist, this is about as complicated as it gets. So it's actually almost impossible for me to ask my physics brethren for help because they don't understand the science. On the other hand, the number of people that understand the science is vastly higher here, as in the science of how those devices work. So I'm much more likely to get help for this from you guys than from anybody else. And so you know, if anybody wants to do it, you know, reach out on the Discord server. And what I would like to do is kind of to have other people do the same thing. And what we're doing is writing this up, and we're kind of going to open source it. What we'd like people to do is to try it with as many different crystals as you can find, right? As many different atomic clocks, as many different ways of doing it as you can possibly find. Because I've done it with my atomic clocks. I did it with a really fancy crystal oscillator that I bought from a company that we're not allowed to export with. So it works with those. I bought these so that I could come here with something, and they arrived on Tuesday. I put them together on Tuesday. I flew out on Wednesday. They work too. So the three things I've tried will work. So I'm now trying to work out if there's something else that we've done wrong that shouldn't make it work. What I would really like to do, if you think of this as LK99 superconductor, right? Most of you have heard of LK99. What I'm really looking for is people who can't replicate it. I'm really looking for people who say, I've tried it and I saw nothing at all. And then I can try the same thing with whatever crystal and whatever setup you've used. So that's what I'd like to do. So thank you very much.
Any questions? Unlock the doors. It's fine. Unbolt them.
So, are there plans available for replicating?
There will be.
Okay.
It's literally like 2 months old.
Okay.
Yeah.
Like for me, like my physics isn't strong, but I have a ham radio license.
Yes, that's what I'm looking for. That's what I'm looking for. Is people who know how to do ham radio and that kind of thing. Yeah, the people for whom an ovenized crystal oscillator is second nature. You know exactly what you're doing with them. Yes.
Any other questions for Ben?
Yes.
Are you using temperature control oscillators?
Sorry?
Are you using temperature controlled oscillators?
Yes.
Okay, so
Yes.
the crystals you're using. Okay.
Yeah.
Yes, ovenized oscillators.
Yeah, ovenized oscillators. Yeah. Any other questions?
Homework sheets are at the back. Thank you very much, Ben. It's been incredible. Thank you.